The age of AI is upon us, and attention inside the transformer module is the reason AI is so powerful today. And flash attention is the algorithm that makes attention fast. Recently, Flash Attention 4 has been released, and it is a good time to revisit the first attention algorithm which started all of this. In this video, we'll go over this Flash Attention algorithm and understand how this algorithm makes attention fast. Hi, my name is Joydeep, and I am a machine learning engineer with 15 years of experience. If you're watching this, please connect with me on LinkedIn and check out my TopMate page. Thank you. In the summer of 2022, when the world was still reeling under the effects of COVID, researchers Tridow and Danfu, while working at Stanford University, were grappling with a tough problem. The attention mechanism in transformers was becoming a computational bottleneck. As language models grew larger and sequences grew longer, the quadratic memory complexity of standard attention was proving unsustainable. Training and inference were painfully slow, and the promise of truly long context language models seemed out of reach. People tried various methods when they changed the nature of the attention calculations, basically to reduce the complexity of the underlying calculations. They were thinking if too many calculations were taking place, can I somehow reduce the scope of the calculations? Sparse attention patterns like long formers selectively masked out certain token interactions. Low rank approximations like performer use clever mathematical tricks to compress the attention metrics. Linear attention reformulated the computation order entirely, but these approaches generally resulted in some speed improvements while sacrificing accuracy. The approximations and modifications meant models couldn't capture the full richness of attention patterns that made transformers so powerful in the first place. The fundamental trade off seemed unavoidable. You could have speed or you could have accuracy, but not both. Interestingly, with flash attention, this turned out to be a mirage. There was a third dimension which people were not considering, and hence they were facing this supposed wall. The trade off between speed and accuracy wasn't fundamental, it was just an artifact of how everyone was thinking about the problem. In this video, we'll talk about this third dimension and how flash attention solved the problem in a very interesting manner. Flash attention was able to unlock a power boost that propelled the field of AI into another level of gameplay. I hope it's not too much gaming metaphor. The moral of the story is that many times what we think of as a bottleneck may not really exist. You just might not be looking at the problem from the right angle. GPUs and memory bounded algorithms. It is common knowledge that if you want to run deep learning models fast, you need to run on them on the GPU. But what exactly is the GPU? A good way of understanding the GPU is to contrast it with the CPU. You want to run fast applications, so maybe you start with the biggest core and plug in the biggest memory to it. But a big memory can be slow to access, so you put in multiple hierarchies of caches in between, such as L1, L2, and L3 caches. Now you might ask, how are caches better than main memory if both are memory? There are various reasons for this. Caches are static RAM and main memory is dynamic RAM. SRAM is and can be considerably faster than DRAM. The values are kept statically, so they don't have to be refreshed, which takes away cycles. DRAM is dynamic, like tiny rechargeable batteries. You have to regularly recharge the ones so they don't drain away and become zeros. This steals cycle time in addition to how you have to access the bits, etc. Being on the same die as or nearer to the processor reduces the round trip. Both L1 and L2 are faster than DRAM from an access perspective. There are a couple of Stack Exchange posts which you should take a look at. I will link to them in the description below. Why do we need multiple levels then? We need cache hierarchy because we are fundamentally constrained by the physical relationship between size and speed on the die. Each cache bit requires transistors and communication speed degrades with distance due to substrate impedance and complex quantum phenomena, creating a trade off where larger caches must be positioned farther from processing units like the memory management unit and arithmetic and logic unit. A single large cache near all subunits simultaneously is impractical because it would consume excessive space and force the subunits themselves further apart, degrading their degrading the communication between them. Instead, processor designers implement a tiered approach. L1 caches are kept small and extremely close to their respective cores for maximum speed. L2 cache provide moderate capacity with slightly reduced locality. And in multi-core system, a shared L3 cache sits between cores, offering substantial storage with reasonable access times for all cores. Basically, there is no sudden drop between just one cache and the high HBM. It's a more gradual drop in performance. When data is needed, the processor searches sequentially through L1, L2, and L3 before accessing slower system memory, then propagates the fetch data back up through the cache hierarchy. This is, of course, just a simple explanation. The actual cache management mechanism in modern processors involve considerably more sophisticated protocols, which is outside the scope of our current discussion. So we have digressed a little bit into caches, but this will be apparent in some time. The important thing to note is that each CPU gets a sophisticated memory management system. Now, if you want to scale up from couple of cores, in CPUs there are only couple of cores, but if you want to scale up from couple of cores to thousands of cores so that you can scale up the computation, there are couple of choices that you have to make. Else your machine will become too costly and you will not be able to sell them in the open to retail consumers or even slightly bigger to you will not be and you will not be able to sell them on the market. The CPU cores are too big. They are quite general purpose, so you can reduce the number of operations they can handle. Here in this Wikipedia link, you can take a look at some of the instructions that are there for processors. Load string double, this one is for store string double, and so on. All this discussion of cores and caches brings us to the difference between compute bound and memory boundedness in terms of algorithms. You can double the number of cores in your GPUs, but that does not ensure that your algorithm will run 2x. For example, let's say you want to run torso sign, it would mean transferring the vector from CPU memory to GPU memory DRAM, which we can call the high bandwidth memory, then transfer to the registers and then doing the actual computation. Once the computation is done, you will transfer it back to the HBM. If there are further computations, then you can keep it in the HBM, or else you will need to move it to the CPU for input-output operations. All this moving data back and forth means that it does not matter if your computations are fast. If your data transfer is slow, your overall latency is slow. Okay, so we have been going over this memory boundedness of algorithms, but what does this have to do with attention? Let's go over the standard attention mechanism and understand the core challenge of attention with the respect to the GPU. So attention is softmax QK transpose divided by root over the dimension into V. So we can write this equation in this standard attention equation in terms of this algorithm that we can go over from the paper. So the standard is we load the QK matrix from the blocks from the HBM and compute QK transpose, write S to HBM, then read S from HBM, compute P equals to softmax of S, write P to HBM, then load P and V by blocks from HBM, compute O equals to PV, write this output back to HBM, and we return the output. The implementation is returned in this way to highlight the amount of memory reads and writes. You can see there are a lot of reads and writes here. Thus, your attention calculation is a combination of both computation and data transfers in memory. If your computation is fast, but your memory transfers are slow, your overall calculations would be slower. Before moving ahead and exploring the core algorithm of flash attention, we will need to wrap our heads around two concepts, tiling and operator fusion. In literature and various blog posts, you may come across the terms shared memory and global memory. This is the same as the caches and the SRAM or the HBM memory that we have spoken to earlier. These caches are called shared memory because the cores don't get dedicated memories like CPU cores get. The meat is that the shared memory is fast but small. Hence, if we want to use some values frequently, then it is better that we somehow fit them into the shared memory instead of relying on global memory. This strategy is called tiling. Let's first go over matrix multiplication by taking the simplest case of a 2 by 2 matrix multiplication where C is A into B, such as here. In the above example, to compute the first element in the output C, this 19 is, as you can see, 1 into 5 plus 2 into 7. In this way, you can fill up the rest of the elements in matrix C as well. Observe that to compute each element in C, you will need to access each element in the input matrices twice. The number of accesses are shown in this green counters at the side. If the program needs to repeatedly access the global memory for each cell computation, then it will be slow. Instead, if we load the matrices A and B into the shared memory, then each element will need to be accessed once from the global memory. The subsequent call can be done from the shared memory itself. Observe that if you generalize this to n elements, the number of memory accesses scale to 2n for the naive case. Hence, the savings in terms of memory go from 2n to just 2 from the global memory. So, what if your matrices A and B are too big to fit into the shared memory? You can divide the matrix into blocks of size, block size into block size that can be fit into memory and then proceed with the computation. For our understanding and to keep the math simple, let the dimensions for all A, B and C matrices be n cross n. Notice that during the computation of matrix C, the result after multiplying a single block of A and B is just a partial sum for C. So for the final result, all the blockwise dot products needs to be accumulated into a final sum. To compute each block in output C, you need k equals to n by batch size iterations. Total iterations for entire C matrix is k cross k blocks into k iterations, that is k cube iterations. During each tile computation, there are two batch size into batch size memory operations. This gives us a total loss of 2k cube into batch size square equals to n cube by batch size. Memory operations. Without tiling, we would need approximately 2 n cube memory operations with each element loaded multiple times from slow global memory. With tiling, we achieve a batch size reduction in memory bandwidth by loading each tile once into fast shared memory and reusing it across multiple computations. This is why tiling is fundamental to efficient GPU matrix multiplication. Let's do a simple benchmarking in this collab code for the tiling concept that we have gone through. First, we'll go over the naive matrix multiplication matmul naive kernel function. The code is written in OpenAI Triton, which feels like NumPy but is optimized for GPUs. This kernel implements a straightforward naive matrix multiplication where each individual thread in the GPU computes one single element of the output matrix C. For each element Cmn, the thread iterates k times, where k is the common dimension of A and B, loading one element from row m of A and one from column n of B, multiplying them and then accumulating the result. This is a direct implementation of the formula Cmn is sum till k times A of mk into B of kn formula. From our discussion till now, you can gather that this approach is generally inefficient because it repeatedly loads individual elements from global memory for each computation. Global memory is slow, leading to high memory bandwidth usage and poor performance, especially for large matrices. Now let's take a look at the tiled matrix multiplication function. This is an optimized version. Instead of each thread computing a single element, a block of threads cooperate to compute a tile of the output matrix C. The key idea is to load smaller block tiles of the input matrices A and B into shared memory. We know that shared memory is a much faster on-chip memory that is local to the streaming multiprocessor on the GPU. Once a tile is in shared memory, multiple threads can access and reuse its elements very quickly without going back to slow global memory. The kernel iterates through k dimension loading block M into block k tiles from A and block k into block n tiles from B, performing a small matrix multiplication TL dot and accumulating the results in a local accumulator ACC. This approach significantly improves performance by reducing global memory accesses. By bringing data into fast shared memory once and reusing it many times, it achieves much better data locality and lower memory bandwidth consumption. Next, we have the wrapper functions matmul naive and the matmul tiled. These Python functions act as interfaces to launch the Triton kernels. They prepare the input matrices, determine the appropriate grid of thread blocks for the kernel, and then invoke the Triton kernel on the GPU. Here you can see they create the output matrix C shape, creating an empty tensor for C and computing the grid dimensions. That is how many thread blocks are needed to cover the entire output matrix. For the tile version, block mn and block k are configurable tile sizes. Next, we have the benchmarking functions. These functions are designed to systematically compare the performance of the naive, tiled and PyTorch highly optimized torch matmul. The benchmark function measures the execution time in milliseconds and calculates the floating point operation per second for a given matrix multiplication function. The run benchmark function orchestrates the entire benchmarking process. It tests different matrix sizes 128 cross 128 from 128 cross 128 to 2k cross 2k, calls benchmarking for each implementation, calculates the speedups and verifies the correctness of the results. If we go through the benchmarking results, you can see that for current LLM matrix multiplication with size 2048, the performance improvement is 378x. One thing I would like to mention is that the code is for educational purposes and will be slower than PyTorch because PyTorch uses highly optimized gem modules. Now, why tiling works? Tiling leverages several principles of computer architecture. There is data locality, which ensures that data being actively used by the processor stays in the fastest available memory, thus maximizing data reuse. There is parallelization, which is that the operations on different tiles of the resultant matrix can often be computed independently and in parallel across multiple processor cores or GPU threads. Then there is vectorization, which is that tiled operations are often designed to be compatible with single instruction multiple data instructions, allowing a single processor core to perform multiple operations simultaneously. The result is a substantial reduction in memory access time and an increase in computational speed and efficiency. So if we have some complex operations, we should look forward to applying tiling as much as possible and thus utilize all our strengths. Generally, if you see, two or more matrices can be tiled and the final output can be calculated in one go. Basic matrix operations such as addition and scalar multiplication are tile friendly. If two or more operations are tile friendly, then you can combine them to compute all operations in an online manner. The advantage is that you don't need to write the intermediate results to HBM, thus getting a speed up in the overall operation. Now if you see the overall attention calculation, it is mostly matrix multiplication. So from our discussion of tiling, we should be able to fuse, you might think that we should be able to fuse them, but there is a problem. So let's talk about the Softmax conundrum. In attention, we first do the Q into K transpose calculation and multiply with the scaling factor tau. This scaling factor tau is generally realized as 1 by root over d, but can be something else as well. Then we seek a mask function in equation 3 that sets some entries in the input to minus infinity and other entries are the same. Then we have the softmax function on these masked values. Then dropout is applied element wise. This means that if your dropout probability is p, then some outputs are marked 0 with probability p and others are scaled down to x by root over 1 minus p. Lastly, this output is multiplied with V matrix. The outputs of equation 2 to 5 are in n cross n matrices. 2 to 5 are in n cross n matrices, while for equation 6 we have n cross d. So n cross n, n cross n, n cross n, n cross n, but n cross d. In the above equation, you can see that equation 2 and 3 can be fused and equation 5 and 6 can be fused, but softmax is different. There is a fundamental incompatibility between the global nature of the softmax function and the tiling strategy to fit large attention metrics into the fast GPU SRAM. Notice that in the softmax equation, you need to know the global sum of all the values in the row to ensure the proper normalization. But in the styling strategy discussed above, you only have access to a small block tile of a row. You cannot know the global statistics for the entire row until you have seen all the tiles. This is a crucial problem that flash attention tries to solve. If we try to make some modifications, so this is an implementation of the naive softmax. If we try to make some modifications in the softmax calculation, we need to keep in mind another issue with the formula. The equation puts a strain on the maximum range our floating point values can hold. The maximum value for float 16 representation is 65,504. So if the value of x is greater than 11, there will be an overflow and our calculations will be wrong and we'll get nans in our result. To get around this fact, we generally find the maximum value of our tensor and subtract this from the exponent. Here is the maximum value. This makes sure that the sum in the denominator is never greater than what the floating point can hold. Doing this is equivalent to this softmax equation. We can multiply, so the derivation is shown here. We can multiply the numerator and denominator with e to the power with 1 by e to the power m. Since multiplication is distributive, this one goes inside. This one goes inside the summation sign. So we can write this as e to the power xi minus m, and similarly we can change the denominator. Based on this derivation, let's discuss the save softmax 3-pass algorithm. So this is the numpy code for this. First we go over the values and find the maximum value. Then we go over the values again to compute the sum of the discounted exponentials. And then finally we compute the final softmax values. Run over this algorithm programmatically in the collab and check the values. Thus there are 3 iterations to computing the softmax values. This creates repeated access in the HBM memory, which is a massive problem, as we have discussed before. We want to reduce this repeated back and forth from the HBM memory. In the flash attention paper, the authors worked out a method to reduce this algorithm to a single pass algorithm and fused it with the other operations in attention. To fix the repeated HBM memory issue in Save Softmax, Maxim Milakov and Natalia Gimelsian came up with the online softmax algorithm in 2018 while working at NVIDIA. In this way, they found a way to compute the maximum and the normalization factor together. In the save softmax equation, if this denominator is given by Li, then we can define the denominator sequence as the sum of the exponentials discounted by the overall maximum value. We want to remove this dependency on n. For this, let's create a surrogate sequence Li dash. So from Li we go to Li dash, where we replace the Mn with the current maximum seen so far Mi. So Mi equals to current maximum till now. This implies that in the final stage, ln is the same as ln dash when the computation for the full vector sequence is complete. So let's find a recurrence relation between Li dash and Li minus 1 dash. So we start with the expression of Li dash. We can write this as I, we make it to I minus 1, or rather we sum to I minus 1. That means that the final I term we can take it outside here, outside of the summation. So this becomes summation of j equals to 1 to I minus 1 xj minus mi, and if we take out this I minus 1, so xj, in the final case xj becomes xi. Final case here the j becomes xi, where j equals to I. So now this one we can write as xj minus mi minus 1 plus mi plus 1. So this one and this one cancels out, so that means it becomes xj minus mi as the same here. Since e to the power a plus e to the plus b is e to the power a into e to the power b, so this part, the constant part, we can take out, okay, and then we can take out from the overall summation. This one is the same, and this one is the same as Li. So Li minus 1 dash is what? As per definition, j equals to 1 to I minus 1 e to the power xj minus mi minus 1. So we can replace it with this one. and thus we can see the overall recurrence relation between Li dash and Li minus 1 dash. Notice that the dependency is always on current maximum Mi and the previous Mi minus 1. So now based on this formula, we can target the computation of the maximum value M and the denominator value L prime in a single for loop. So now from our 3 pass we have the 2 pass algorithm. Notice that the current maximum Mi and Li are computed within a single for loop. The L prime value is in accordance with the relation that we just derived. Compare the correctness between the 3 pass and the 2 pass algorithms and ensure that the output matches correctly. However, notice that we are still in 2 pass, so there is pass 1 and pass 2 over the full data. So the obvious question is, can we now reduce to a single pass to minimize global I/O? The answer to the above question is unfortunately no, but keep in mind that we don't really require the softmax output. The intermediate outputs are not required. What we really want is the final attention output O, as shown in this equation. In the flash attention paper, they worked out a way of finding the output in a single pass using the same surrogate trick described that we have worked out just now and came up with a recurrence relation. To understand that, let's go over some of the notation. So Qk is the kth row vector of Q matrix. K transpose is the ith column vector of the K transpose matrix. Of K colon is the kth row of output O matrix, and Vi colon is the ith row of V matrix. So this is the row and this is the column part. So using this notation, we can write the same 2 pass algorithm here. In the first loop, we compute the ith attention logit xi as the dot product of the kth row vector of the Q matrix and the ith column vector of the K transpose matrix. As we process each logit sequentially, we maintain a running sum Mi by comparing the previous maximum Mi minus 1 with the current logic xi. Simultaneously, we update the surrogate denominator Li dash using the clever rescaling formula. Li dash equals to Li dash minus 1, rescaling it with exponential of previous maximum minus current maximum plus exponential of xi minus m that we had derived just now. By the time we finish this pass at I equals to n, if I equals to n, we have computed the true maximum mn and the final denominator ln dash is equals to the true softmax denominator ln. In the second for loop, we use the computed statistics to calculate the actual softmax probabilities and the final output. For each position I, we compute the softmax score AI as the exponential of e to the power xi minus mn divided by ln dash as shown here. Then we incrementally accumulate the output y as the running sum for the multiplication between the score and the V, where each term represents the weighted distribution of the jth row of the value matrix V. When this also has reached the final stage, which is exactly the kth row for the final output matrix O, or rather we have computed the kth row for the final output matrix O. This two-pass approach efficiently combines the computation of softmax statistics and the attention output while maintaining numerical stability and enabling online processing. Now, if we replace this definition of AJ from here, we get this equation. The equation has dependencies on the global values of M and L dash. So let's play the same surrogate trick that we played before and create an intermediate output OI dash where we only depend on the current maximum MI and the current softmax denominator Li dash. So we are defining the OI dash here. This means that in the final case ON dash MI becomes MN and Li becomes Ln dash, and thus we can say that On dash is the same as On. Let's see where this leads us to. So now let's take this OI formula and break it down similar to how we had done in case of the two pass. So similar to before, we can break down the definition of OI dash to the current contribution at position I and the sum of all previous softmax weighted value vectors from j equals to 1 to I minus 1. In the next equation 23, we strategically write the summation from j equals to 1 to I minus 1 by introducing a clever rescaling factor. For each term in the sum, we multiply and divide by exponential x to the power j minus mi minus 1. So this one is here, but this one and this one, they can cancel out. So it will basically be the same. Other terms are same. Moving on to the next equation, we factor out the common rescaling factor from the summation. So this part, we take it outside in this bracket, and this one overall we can write like this. So xj minus mi minus xj minus mi minus 1, and this one will be, this one too is constant part. So this one is a simple subtraction in the exponent. Now finally this one is OI minus 1 dash as per definition. This one and this one cancels. So we can write it like this: e to the power mi minus 1 minus mi. This one is here and this part is here. So overall we have got this nice formula. This shows that we can compute the current output by taking the previous output OI minus 1. So the current is previous output, rescaling it by a factor. So this is the rescaling factor which corrects for the updated statistics, and adding a new weighted value, and there is this new weighted value. So you can see that the current recursive formula is only dependent upon Li dash, or and the previous Li dash, the current running maximum and the previous running maximum, which makes this a simple online formula. No need to compute the global values. There is no mention, no global value dependency. Now based on this derivation, we can write the final single pass algorithm. This is the final single pass algorithm where we compute all the required intermediary states in a single pass. So for I in so the I in x value is the row value in Q multiplied by the transpose of K. We find the current maximum. We update the denominator as per the rescaling, as per the formula we had derived. and then we find the attention scores. So finally we have the output for the kth row and we write it to memory. Notice in this algorithm that the intermediate states have a small footprint and can easily fit into the GPU shared memory. Thus, the above algorithm allows us to incrementally update the output as we process each new position without needing to store all intermediate softmax values or recompute everything from scratch. The rescaling factor ensures numerical stability by adjusting all previous contributions whenever the running maximum changes, while the denominator ratio ensures the softmax probabilities remain properly normalized. Observe that all these operations are associative, meaning it does not matter which cell and corresponding rows and values you are computing right now, or you can compute them in any order. This means that the above algorithm is compatible with tiling. So let's go over the algorithm as we have seen in the flash attention paper. So this is the algorithm as given in the flash attention paper. For the algorithm, we need the QKV matrices to be present in the HBM and assume that the SRAM on the chip is of size M. This means that the SRAM can hold M floating point numbers. We can also assume a softmax scaling constant to be tau. There is a masking function mask and the dropout probability is p drop. Next we generate a pseudo random number generator R. In standard attention implementations, you could generate dropout masks once and store them. However, flash attention recomputes attention during the backward pass to save memory. So during forward pass, we generate dropout mask using R, apply it, save R state. So this R is used to restore and regenerate the exact same dropout mask. In the next line, we set block sizes BC as the ceiling function of m by 4d and row wise batch as the minimum of the ceiling function of m by 4d and the nd. This calculates the block sizes that determine how the input matrices QKV are divided into smaller chunks that fit in SRAM. The D here is the head dimension of the QKV matrices. BR means that it is a row block and BC means that it is a column block. We are dividing by 4D because to account for the memory needed to store 4 blocks each for the Q, K, V and O blocks. While this minimum with respect to the head dimension prevents the row blocks from being larger than necessary. Since attention typically works with sequences, there is no benefit for making row block greater than head dimension from a computational perspective, as it might waste memory. Next we initialize the O, L and M in HBM memory so that we can populate the values once the computation is done. We also divide A into TR blocks of size row block into head dimension each and divide L into TR blocks of size row block each. This divides the output and statistics to match the Q blocks. So Q blocks are also being divided here. So Q is being divided based on this and KV is divided based on TC blocks. Why we are doing the alignment in this way? Because each QI block produces a corresponding output block OI. Each row of QI needs its own statistics Li and Mi values. This allows processing one Q block at a time while updating its corresponding values. Now we are ready and can do the calculations, the actual calculations. So now we are ready and can go to the calculations. In step 7, we load the jth column of k and the jth column of v from HBM to SRAM. These blocks are used across the full inner loop, iterating over all Qi blocks. This means that the Kj and Vj stay in SRAM while we iterate through all Q block. So here over full here J, Kj and Vj. In step 10, we have the unnormalized attention scores between the current Q block and K block. Step 11 is the mask function implementation. Notice that masking is a cheap operation, element-wise comparison and assignment, and thus can happen directly on chip in SRAM. Next, we compute the local statistics Mij, which is the max score in this Qi-Kj block, and Lij, which is the sum of the exponential scores in this block. Then in step 13, we update the global statistics Mi, which is the running maximum score we have seen so far across all K blocks processed. Then in step 13, we update the global statistics Mi, which is the running maximum score we have seen so far across all K blocks processed, and Li, which is the running sum of exponential scores seen so far, properly rescaled based on the local statistics computed so far. In step 14, we apply the dropout to the unnormalized attention weights. Notice that we are applying the dropout on the unnormalized weights and not on the normalized attention, which is still being computed. We will normalize them later when we have the final Li. This is fine because applying dropout before final normalization is mathematically equivalent and more efficient. Step 15 is the crux of the whole algorithm and the raison d'etre. Here we are computing OI based on this equation that we had derived earlier and writing it to HBM. Finally, in step 16, we update Li and Mi. Based on the Triton Lang implementation for flash attention and to make it compatible to run on the free tier for Google Colab, we can write the flash attention implementation for Tesla T4, which is a Turing. So Tesla T4 is a Turing SM75 architecture and has shared memory 48 KB. In the code, we have the function flash forward inner, which runs inside the flash forward kernel and implements the lines 10 to 13 of the algorithm for one column block at a time. The stage constant expression selects loop bounds at compile time, stage equals to 1 visits all column blocks and is non-causal. Stage 2 visits only the diagonal block where the triangular mask is actually needed. This avoids applying the expensive TL.where mask on every block when only one block needs it. In each iteration, we load Kj. This computes Qk, which is Q into Kj transpose, then applies the exponential. Here we are computing Qk, which is the Qi into Kj transpose, and then applying the softmax. and then applying the exponential trick from the tutorial. We'll talk about what is this QK scaling later, but essentially we are using exponential 2 instead of actual or log or the natural exponential for cheaper hardware instruction. The online Softmax update from the algorithm we had discussed then follows directly, where alpha is exponential of mi minus mij, rescaling the old accumulator before adding the new block's contribution. V is loaded after P is computed rather than before to let the compilers reuse the compiler reuse the registers. The function returns updated accumulator Li and Mi, thus avoiding HBM writes inside this inner function. The flash forward kernel is the main kernel call. Here we take the 4 individual strides of the original batch, head dimension, sequence length, and detensor. Then pointer arithmetic is used to reach this program's instance, batch head slice. The offset AZ encodes the flattened batch head index and dividing by H recovers the batch and head indices separately to apply their respective strides. Then the accumulators ACC, Li and Mi are initialized. We are initializing Li to 1 rather than 0 is the fix for a subtle bug. On the first iteration, Mi is infinity. First iteration, Mi equals to minus infinity. The flash forward kernel is the main kernel call. Here we take the 4 individual strides of the original batch, head dimension, sequence length, here we take the 4 individual strides of the original batch, head dimension, sequence length, and detensor. Then pointer arithmetic is used to reach this program's instance, batch head slice. The offset AZ encodes the flattened batch head index and dividing by H recovers the batch and head indices separately to apply their respective strides. Then the accumulators ACC, Li and Mi are initialized. We are initializing Li to 1 rather than 0 is the fix for a subtle bug. On the first iteration, Mi is infinity. First iteration, Mi equals to minus infinity. So alpha equals to exponential 2. So here Mi is infinity. So alpha equals to e to the power minus infinity minus Mij equals to e to the power minus infinity equals to 0. Initializes, meaning the old ACC contribution is zeroed out correctly. But if Li equals to 0 and the first block happens to be entirely masked, then Pij is all 0. Lij equals to 0 and or rather Li stays 0, causing ACC divided by Li to produce nans. Starting at 1.0 provides a safe denominator. Then after loading Q, the flash forward inner is called. Once for non-causal, stage equals to 1 full range, and once for the diagonal block. Once for non-causal, stage equals to 1 full range, and once for the diagonal block, stage equals to 2 for causal. A complete causal implementation would also call with stage equals to 1 restricted to high equals to start m into high start m into block m for the off diagonal blocks, but this simplified version only handles the diagonal. Finally, we update the mi and acc. The first line computes log2 sum j or the standard log sum exponential by combining the running max and the log of the normalizer into a single scalar per row. This is what gets stored in the M buffer and is needed for the backward pass to recompute softmax probabilities without storing the full attention matrix. The second line applies the full final normalization. The output is cast from FP32 to FP16 only at the TL store call. Notice that all internal arithmetic is in FP32 till now. You can compare our kernel with the flash attention original kernel as shown in the flash attention repo. There you can see it's a single function call and many improvements are made because we have the flash attention 2 as well. Still there are many insights we can get from the code. Till now we have been discussing the forward pass, so we'll discuss the backward pass as well. Suppose there is a scalar loss function L, and we are working in because we are working in a deep learning framework such as PyTorch, we will be having the output gradient. So the output gradient DO is there, which is partial of DL based on DO, which belongs to real number and cross D. So this will be there. From this we want to compute the input gradients dq, dk and dv. So we will have dq, dk and dv, where dq is dl by partial dq partial of L by k and partial of L by dv. So to be able to achieve this here, so for DO we have, so the output is for attention, so attention is there in the middle, so this is how the gradients will propagate. So there will be the backward pass calculation where we'll apply the chain rule pass to these three calculations. In the paper the derivation is there, but a lot of steps are skipped. In linear algebra, it is important to make sure that we are differentiating in the right manner. Hence, taking inspiration from Lee Wan's blog, let us take a 3 by 3 matrix example to make sure that our expressions are correct. So we start with P, V and O matrices, where P is P11, P12, P13 and so on. So P matrix will look like this, V matrix will look like this, and O matrix will look like this if they are 3 by 3 matrices. Let's assume that QKV are all 3 by 3 matrices. So from equation we know that P equals to softmax of Q into K transpose. Hence P is 3 by 3 and DO is partial of L by partial of O. So this is also 3 by 3. So ignoring the dropout part for now, O is PV. In the next line we can expand this. Each element is the multiplication of the corresponding elements from rows of P and columns of V. This is shown by the subscripts. Now let's focus on finding dV first. Remember that V is a 3 by 3 matrix and L is a single scalar loss number. So when we write partial dl by dl dv, we are asking how does the loss change with respect to each individual element of V, or rather how can we find the partial derivatives? For this we can go over this Stack Overflow post. The point of derivatives in one variable is to provide linear approximations fx equals to fp plus f dash p x minus p plus of x minus p to nice functions. Multivariate derivatives work the same way, except linear approximation here means approximation by a general transformation or a matrix transformation instead of a scalar. This is made precise by the following definition. We can say that a function which transformed from linear space in n to linear space in m has a total derivative, a linear transformation, same from Rn to Rm, at a point P if there exists epsilon greater than 0 and a function EP of h defined such that h less than epsilon, such that when we change f of p with h, it should mean that there is some fp plus some derivative of fh and a transformation of that, where limit h tends to 0, ep of h equals to 0. The matrix D of fp is sometimes called the Jacobian. So this is the Jacobian. In little o notation we write like this. This might seem unnecessarily complicated, but it is the key to understanding the multivariate chain rule. So now if this is composing functions, that means we will do this, replace this by this as from here. So then if this linear transformation is there, so that means that we can remove the bracket. So this becomes g of fp, this derivative of h, or in other words the total derivative d of gfp of gf at p is the matrix product of the total derivatives dg and dp. So this is a matrix transformation. So generally this relationship of partial derivatives is taught as tree diagrams, but basically this is the most general statement of the multivariate chain rule, The relationship to tree diagrams is that one can model matrix multiplication using composition of incidence matrices which come from graphs depicting incidence relationships between sets. So this means that to find the partial derivative means resolving the derivatives through all paths to reach their partial derivative. So let's focus on finding dv element by element. We start with partial dl dv11. We will start with partial dl dv11. Now L doesn't depend on v11 directly. It depends on v11 only through O as shown. It only depends on v11. It depends on v11 only through O as shown in this figure. So using the multivariate chain rule to find how L changes when v11 changes, we need to account for every path through which v11 affects L. So observe that in the expansion of O, there are three elements that contain v11, which is, so this one v11, v11 and v11. That means O11, O21 and O31. So we take these three values. So we are writing these three values here. That means if I now take partial O11, partial O21, then this one gets cancelled and we get only P11. Similarly, for partial this by partial V11, this one goes away, and partial O31 divided by partial V11, this one goes away, and we have only this one and this one. This is what I have written here, which means now I can write partial L partial dl dv11 is, from the chain rule we go through all the paths. So the path through O11, path through O21 and path 3 O31. So this is the O11 path, O21 path, O31 path, which means from here we can replace this one by P11, this one by P21, this one by P31. So now we can write dv11 is P11 do11, P21 do21, P31 do31. Using similar logic as we have done for dv11 and using the same multivariate chain rule, we can expand for the other elements in the matrix dv. We can expand for the other elements in the matrix dv. From dv12 to dv13. And then using the same logic we will arrive at these sets of equations. Try it out on your own and see if it matches with the ones shown in the equation. So now what we can do is we can replace these expansions for dv11, dv12 and so on in the overall dv matrix, and so from here we can write it in this way. So as you can see, If I write it as a matrix multiplication like this and like this means that P11 DO11 plus P21 DO21 plus P31 into DO31, which is the same as what we see here. So this one we can write it as a matrix multiplication of this one, and as you can see this is P11 P12 P13 P21 P22 P3. So this means that this is now you can see that this guy means this one P transpose and this guy means DO. This guy we can write as DO. The gradients of dq and dk are slightly more complicated, so we need to go through the gradients of dp and ds first. Now dp is partial of L by partial of P or partial dl by dp, which we can expand in this way. So partial dl by partial or partial dl by dp11, partial dl by dp12, partial dl by dp13, and so on. So using the same multivariate chain rule, if I want something like partial of L by partial of P11, P11 is present in O11, O12 and O13. So partial of dl by dp11 is, we can write it in this way. So this is the O11 path, O12 path and O13 path. Similarly, partial of dl by dp12 goes through the O11 path, O12 path and O13 path, and so on. Partial of partial do11 by dp11 is this guy, this one gets cancelled. Similarly, partial of O12 by dp12 is or dp11 is this one gets cancelled, and partial of O13 by dp11 is V13, this one gets cancelled, which one we can write this here. So partial of do11 dp11 is v11, partial of do11 by dp11 is v12, and partial of do13 by dp11 is v13. Similarly, we can write for other parts as well, and so on. Now partial of dl by do11 we can replace with do11, this one we replace with this one we replace with this one, and so on for the other parts in the matrix as well. So now if we take this as the row values and this as the column values, so the do1 with do12 do13 come in the row, and v11 v12 v13 come in the column. So v11 v11 this one, you can see these are the same, so they come in the column. This v21 v22 v23, so again this in the column. So overall this matrix we can write it in matrix multiplication form like this, and overall this is like v11 v12 v13 v21 v22 v23 v31 v32 v3. So this is like this. So we can write this as do into v transpose, which is actually what we have for dp. So this guy is dp. Now let's go over the derivation of ds as well. We know as per definition, so this is by definition, P is softmax of S. So we can expand P in terms of matrix terms. This is P11, P12, P13, P21, P22, P23, and P31, P32, P33. And S is S11, S12, S13, S21, S22, S23, S31, S32, S33, which means that softmax of for example, so this guy is softmax S11, right? So exponential of S11 divided by sum of all the exponentials in the first row. Similarly, this is softmax of S12 and so on. This means that applying the same multivariate chain rule while deriving dv for ds, we can say that the first value partial dl by ds11 is the sum of the partials going through, let me show here, is the sum of the partials going through P11, P12, P13, because these are the same values which have the terms. So P11 has S11, P12 also has S11, and P13 also has S11. So to find partial dl by ds11, we need to find partial dp11 ds11, partial dp12 ds11, and partial dp13 ds11, which we don't know here. Now observe that partial dl by dp11, I mean this and these values are known. From here we have found, right, this is the same as this. So it's known from here. So it's known from the above equation. So let's go over these values one by one. First, let's go through this value, partial dp11 by ds11. Now p1 we know that it's basically p is softmax, like we just saw, right? Softmax of s, which means that p11 is exponential s11 divided by sum of the exponential in the below row. So p11 is the exponential s11 divided by sum of the exponentials in the below row. And we know from our calculus classes that if ft is a fraction gt by ht, that means that derivation of ft is derivation of gt ht minus gt will keep ht derivation divided by h square t, right? So if you know this, that means that this is the numerator, this is the denominator. So derivative of the denominator into numerator we keep it, sorry, derivative of the numerator divided by denominator we keep intact, minus the numerator we keep intact and we take the derivative of the denominator divided by denominator square. Now derivative of exponential is the same thing, we keep it, and in this derivative this one goes away, only this one gets, so we keep it like this, and we can multiply it this one, so exponential becomes exponential. That means or rather if we separate out the minus, then this part comes here, denominator this one and this one square gets cancelled, so this, and this is also a square and this one is also square, we take a whole square. This one, if you observe, this is the same as p11 as we have seen here, and this one is p11 square. So partial dp11 by ds11 is p11 minus p11 square. Using the same logic, we can find for p12, so p12 is this, and then we take the derivative. Now here derivative of, so this is the exponential of s12, so the derivative of the numerator, oh sorry, s11, so this one turns out to be 0, and we keep the numerator the same and take the derivative of the denominator here, so the derivative of denominator is exponential s12, so this turns out to be that partial dp12 by ds11 is negative p11 p12. This we can find because we can, so p11 is this one divided by one of the values, so there are two values here, so one of the values, so which is p11, and this one we take as the other value p12. Similarly, you can find partial dp13 by ds11 is negative p11 by p13. I am not showing the derivation here, but it's similar logic. If you have understood the steps just now, then you should be able to derive this yourself. Which means, going back to this expression, We have just found out these three values, right? We can plug it in now. So partial dp11 by ds11 is p11 square. Partial dp12 ds11 is negative p11 p12, and partial dp13 by ds11 is negative p11 p13. Do you see the pattern here? If we do the same pattern, so partial dl by ds11, wherever the subscript is matching, it will be like that specific subscript minus the subscript square, otherwise it will be negative, like cross negative, right? So that is why p13, this one is p13, this one is p13 minus p13 square. So it could have been minus p13 p13, but wherever is the same, you get a p13 minus p13 square. So we get all these values. You can try and see to derive this yourself. It's the same steps. Which means for partial dl by ds, I can now plug in all the values. Since I have all the values, I can plug them in the matrix form. Now in the previous cases, we were able to nicely separate out in matrix forms. But in the case of S, if you are hoping to do that, sad news is we will not be able to do this in the case of S. So we'll consider them row wise. So I'm going to write this one in a row wise format like this. So, and this becomes like a column matrix equation. Partial dl by ds is partial of dl by ds1, dl by ds2, and partial dl by ds3, which means partial dl by ds1 looks in row form like this. It's a combination of this one, and this one. So this equation is just taking the first value of the column vector and showing it in expanded form. If I decompose this vector, so this p11, this one, I can write here, this one, take out the row vector. If I take out this row vector, then this one, so these values come here and these values come here, right? And if I take out these values from this overall matrix, I get this one. So basically trying to take out the individual values and the multiplicative values, and I can take out the subtraction minus sign also here, and this one becomes partial dl by dp1. This formulation will soon help us. Let's see. Notice that P11 is not here, so that is why this one becomes 0. In the next step, we can remove the bracket, so this one comes here and here. Now after we make the broadcasting, we convert this first partial dl by dp1 back to this row vector partial dl dp11, partial dl dp12 and partial dl dp13. As we intend to do the multiplication after this, for the second term, notice that this overall matrix we can decompose into the multiplication of a column P11, P12 and P13 and this row vector P11, P12, P13. So P11 into P11 is P11 square. This one is this guy is this is this is this, is this is this, this is this, and this is. Now see, if we multiply this row vector and the matrix in the first term, we get something like this, right? And the second term, we can write it as P1 transpose into P1, right? This is what we are writing here. So we arrive at this final form. Now consider this first part. We can write it as element wise multiplication partial dl by partial p1 into or element wise multiplication with the row vector p1. So this is what we are doing here, and this guy we keep as it is. Now notice from our previous derivation of dp, we can write this as, so dp is partial dl by dp is partial dl by do into v transpose. Now this equation holds if I take only the row vector one at a time. So this is what we are arriving at here. So if I take that and replace this partial dl by dp1, we get dl by do1 into v1, sorry, this is the full matrix. So v transpose, and then we write the remaining ones. So this is what we are doing here, and we know that x transpose y transpose is the same as yx the whole transpose. We revert it and then take this one. So this part we can take bracket and we can write it as P1V transpose. Now we know that as per definition, O is P of V, P into V. So O1 is P1V, which means I can take this and write it as O1 transpose. This is what I am doing here. Now notice that all the terms, this, in this expression is in terms of the first row vector. To simplify a little bit or make it more in line with what is written in the paper, let's define the term D, and the row D1 stands for partial dl dO1 into O1 transpose. Now if we take the multiplication of a row vector and another, so this one becomes then a column vector after taking the transpose, we can say that it is the element wise multiplication of the same two row vectors and then doing a row sum. Make sense? So it's like A1, A2, A3, and if I take B1, B2, B3, which means this into this into this, and this into this, basically A1, B1, A2, B2, A3, B3, and then we do a plus, right? So it becomes like a element wise multiplication and then we do a sum, right? So we can write it in this way. So if we define this in this way, we can replace this part with D1, or rather, yeah, D1. Now this D1 is effectively a scalar. So when we are writing D1, we can write it as element wise multiplication. So now this overall expression, all the individual elements are element wise multiplications, which means we can take this P1 out, which would convert this to one subtraction and one multiplication. Now here we did row wise. If we convert that into element wise, we can write it as S11, P11, P11 we give it here, but this we have to materialize, or we are depending on having the D value for the full row. Now if you are sad that we are not able to do a full streaming like we did in forward pass for Softmax, at least there is the consolation prize that this D1 is actually a scalar. In the actual algorithm, later on in the actual algorithm, you will see that we will do something like a partial, or will calculate this previous and then do that. But real optimization is something that you might think of. Similarly to how we have calculated the DS for each, I mean this is for S11, right? We can extend this to all the values of S in the matrix. So we know S, the overall DS, and we can attempt dq and dk. Let's go through the derivations. So now let's take a jab at dq and dk. And dk, as per definition, as defined, S is q into k transpose, which means in expanded form this becomes, so S we can write as S11, S12, S13, S21, S22, S23, and so on. And Q into K transpose is, so Q is, we can think of it as this way, right? Q11, Q12, Q13, Q21, like this, right? And K is K11, K12, K13, like this, right? Sorry, K21 and K31, right? So Q into K transpose means this into this, because this one will become column. So Q11 into K11, Q12 into K12, Q1 into Q13 into K13. Similarly, Q21 into Q11 into K21, Q12 into K22, Q13 into K23, and so on. Make sure that you understand this part. Which means that if I take partial dl by dq11, so dq11 is here, here, and here. So, and which is, this one is S11, right? This one is S12, this one is S13, like you can see here. So it's these values, right? So that is why our partial differentiable equation will go through S11, S12, and S13 as per the multivariate chain rule. Now if I do the differentiation, partial ds11 by dq11 is, q11 is here, so this gets cancelled, so we are only getting k11. Similarly we get for this one k21 and for this one k31, so this one, and you can see here this one, right? Similarly we can get the equation for partial dl by dq1 2, dq13, dq21, dq22, dq31, dq23, dq31, dq32, and dq33. Make sure, try out the derivations and check your answers. So if you see this, partial dl by dq, so let's, if we consider the values in a row, so in a row s21, 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 3s2, 3s2, 3, k11, k12, k1, k21, k22, k23, so it comes like this, right? So basically you can write it like this, L by s21 partial dl by partial s33, so this is the vector, and the other, so if I multiply in the column, k11, k12, k13, k21, k22, k23, k31, k32, k33, right? So if we compile all the equations in the matrix form, we get like this, which means finally we can arrive at partial dl by dq is partial dl by ds into k, or I can write dq is ds into k. Now ds we had already calculated or derived before, right? So and of course we have k from the activation, so dq we have, or we can get at dq. Similarly we can go over the derivation of dk. It's very similar logic. We start with the same s equals to q into k transpose. We decompose the overall equation and then we find the matrix form. Here the difference is that here S11, S12, S13 comes like this. So that is why this becomes the transpose. So dk becomes ds, you take the transpose into q. So now we have derived all the required equations for all the backward pass values, and we can combine them and write it in this way. So dv is p transpose into do. So p and output derivations we know. So we can start with dv and get p transpose into do. dp is do into v transpose. So both of these we know, so we can compute dp. Since we now have dp, we can compute ds, which is p into dp minus row wise di. So ds is dependent on dp, and once we have computed ds, we can compute dq and dk. So dq is ds into k and dk is ds transpose into k. So from these equations you can understand the backward pass, right? At least the naive version of it, which means compute dv and save to HBM, compute dp and save to HBM, compute ds and save to HBM. Finally, these are independent. So computing dq and dk probably together as they depend on ds, and then save to HBM. So instead of computing the backward pass like this, the authors of the flash attention paper were able to find a tiled approach to the backward pass, which we will discuss next. So this is the flash attention backward pass. Similar to the discussion on the forward pass earlier, let's go through this line by line. So let's start with the requirements. As we have just discussed, for the backward pass we need QKV output and the derivation and the DO output present in HBM memory. We will need the vectors L and M, which are part of the real numbers, which are the log sum exponential and max values from the forward pass. These also stored in HBM memory. We will need the hyperparameters also in SRAM, tau, which is the softmax scaling constant, the p drop, which is the dropout probability, and the masking function mask as defined in the forward pass. For the state of the algorithm, we need R, the pseudo random number generated state. This must be the same as the forward pass so that we can reproduce the dropout mask. Now steps 1 to 5 is about setup. We initialize the RNG to the same state as used in the forward pass. This is important because we want to reproduce the exact dropout mask that was applied during the forward pass. This ensures that the gradient computation is consistent with the elements that were actually dropped. In step 2, we set the column block size BC and row block size BR. As seen in the forward pass, the factor of 4 is to account for all the intermediate matrices in SRAM simultaneously. Using this in steps 3 and 4, we partition Q and uh, Q and K and V into the ceiling of n by BC. Thus, TC is the number of column blocks to cover all n tokens. Similarly, we divide O, DO, L and M into TR equals to ceiling of n by BR blocks, where TR is the number of, so we know that TR is the number of row blocks. Similar to the inputs, we should be initializing the outputs as well. So DQ, so we zero initialize DQ in TR blocks and KNV in TC blocks so that they match KV's column wise processing. This is done so that we can accumulate results as we go. Similar to how we had seen in the forward pass, there is this overall nested loop structure. So J means looping over column blocks and I means looping over row blocks. So that means this double loop processes TR into TC block pairs. So this outer loop J iterates over K and V blocks column wise chunks, so that is why this is column block, and the inner loop I iterates over QO DO blocks. Thus with each IJ we compute attention over QI and KJVJ. Now if you compare the forward pass with the backward pass, many of the operations are the same. Computing the attention score S equals to tau Q into K transpose is the same in step 12 in backward and step 11 in the forward. The same dropout is applied to both attention probabilities. So mass function is here. The only difference is that in case of backward, the dropout mask Z needs to be the same that is applied in forward, and then pointwise multiplication is done. So still step 15 in backward, the steps are mostly similar to the forward process because the same tensors are recomputed. Since this is the backward pass, we have to compute dv, dp, ds, dq, dk. This is done between steps 16 to 22. In step 16, we are computing dv as per our derivation. Since this is a tiled algorithm, we are accumulating dvj contributions from all query blocks di, from all query blocks I. Next we had derived dp is do into v transpose. So we implement the algorithm for computing dp. Since the chain rule for the gradients is loss goes to do goes to dp dropped before after that only we go to dp, then ds, then only we arrive at dq and dk. Hence this calculation is for dp dropped. After that we need to apply the dropout z to arrive at the actual dp. Next, if you remember, we had next we need to define or calculate di as the row sum of do with element wise multiplication of o. So this is what we see here. Notice that although we are loading one full row of o, this can be done element by element in a vectorized form. Now once di is there, we can calculate ds. So we are applying the ds formula here. Notice that ds is calculated element by element, hence it is dsij. So as we calculate dsij, we update the value of dq and dk. So we accumulate, and also we accumulate for dq and dk. So this is as per this formula here. Thus we have implemented all the expressions that we have derived for the backward pass. We write the dk and dv value for that specific column to HBM, and once all loops are done, we return the three gradient matrices. Now let's go through the code for the backward process. So in this Colab notebook, I have implemented the backward pass algorithm as we have discussed. Although this code is shown in Colab I just had a T4 instance, but I could not run it in T4. Only the forward pass runs in T4. I had actually created an H100 instance and ran it there. So do keep a note of that. So during the backward pass calculation, the calculation of ds is dependent on di, where the dependency is only on o and do and not on k and v. So we can compute this upfront and store it in HBM as a reusable buffer. The alternative would be to recompute it inside every iteration of the hot dk dv inner loop wasting compute and register pressure. So we have this function attention backward preprocessing, and here you can see we are calculating the delta and storing it in the delta pointer. In the forward pass, the loop structure was straightforward. For each Q block, stream over all K and V column blocks J, and then accumulate the output completely before writing to HBM. But things are different in the backward pass. There is a different dependency structure. Now we can try to write all the operations on a single go, essentially opting for a fused kernel. In that case, we are writing for each ij block, computing all the 3 gradients simultaneously. We would be writing partial DKDV buffers and reducing afterwards. Thus the overall memory would be required would blow up. As a solution, 2 separate kernels are written. So as a solution, two separate kernels are written. One is the attention backward DKDV, and attention backward DQ. One would do, as obvious, one would do the DKDV together and another would, and this one would work on the DQ part. So let's go over the DKDV part. Here we are streaming over all Q row blocks and accumulating DKJ, DKJ and DVJ. We start with QK transpose, which is the dot product of K and Q transpose, and then we calculate the P transpose. Notice here that Pij is never stored. We are computing it on the fly from the saved log sum exponential m. The Q transpose pointers has the shape, head dimension and block m1 in index space. The dimensions are swapped relative to the block m head dimension layout. That means that the dimension here is block n1 block m1 without needing an explicit transpose TL dot transpose call. Thus we are able to directly arrive at PT. No need the additional transpose call. Because this variable is already transposed, rows are key block positions j, columns are query block positions I. We have to specify the causal condition as I greater than equals to j, which means that query tokens can only attend to key tokens only if the key comes before or at query position. So the zeroing mask here before accumulating into dv and dk ensures these positions contribute nothing to the gradients. This is consistent with how the causal mask is applied in the forward pass. For the dk calculation, we load di in the delta vector block m1 this is pre-computed by the attention backward process. We compute the derivative of P transpose dpt, which is the dot product of V and DO transpose. This is as per the equation we derived, and we calculate DST, which is P transpose into dpt minus di when broadcasted. So these are as per the equations. Then we calculate dkj and accumulate into dk. That is why this plus equals to is there, which is accumulation. So these are as per the equations here. Next we move on to the dq inner loop. This is the mirror image of attention backward dkdv above that we discussed above. Before in dkdv we fixed j and streamed over the query rows. Now we are fixing I and streaming over the kv column blocks. In this function we are basically implementing this dq is accumulation of over with multiplication of ds into k. Another difference is in the calculation of di. In the above function, di you can see is inside the loop. So this guy is inside the loop, but in the dq calculation di is loaded outside. This is because m offset changed each iteration as the function stepped through different q row blocks. Here offset of m is fixed for the entire function call. This is the current row block that we own. So di is loaded once before the loop and reused across all number of steps iterations. Thus we are saving number of steps HBM loads for di compared to attention backward dkdv. Also for the masking we need the query row index greater than key column index. Thus this condition is the standard causal mask in the natural or non-transposed orientation. The other calculations such as the ds calculation, dp, and of course we apply the calculation of dq, mostly identical to above, and we apply the dq calculation here. Next we go to the outer glue that dispatches to the two backward functions that we have discussed now, dkdv and dq, which is the kernel that PyTorch AutoGrad actually launches. This attention backward orchestrates the entire backward pass by calling first the attention backward preprocess, or rather attention backward preprocess is called or had been called earlier in the backward pass. And once we do that we go to the attention backward calling here or the main backward kernel. Inside this main kernel we are calling the dkdv and the dq. So in first in axis 2 we index the flattened batch head pair, and index 0 is to identify which kv column block this instance owns. So the total number of program instances is n by block N1 into B into H, meaning every KV column block for every batch head pair runs in parallel. Because dk and dv are indexed by j, the choice is to index by j rather than I, or KV column block rather than the Q row block. This gives each instance exclusive ownership of 1j and avoid any write conflicts when accumulating those gradients. K and V for a particular column block are loaded once and stay in SRAM for the entire dk-dv section. For the entire dk-dv section, we initialize dv and dk to 0 and accumulate contributions from every Q row block. Thus, we have one block N1 head dimension for tile each for K and V resident throughout rather than reloading them for each Q query block. So the next section is the dk-dv calculations. K and V for a particular column block are loaded once and stay in SRAM for the entire dk-dv section. dv and dk are initialized to 0 here and will accumulate contributions from every Q row block. In the causal attention case, column block J, so this is the causal attention case. Column block J, which is at position start n, can only receive gradient contributions from query rows I greater than n. The diagonal block where query row and key column indices overlap needs a per element triangular mask. That is why we call the attention backward dk-dv with mask equals to true for just this diagonal section using the finer tile size. Mask block M1 is block M1 divided by or integer divided by block slice factor. The finer tile is needed because within the diagonal block only half the elements on average are unmasked. The idea is using a smaller block M1 reduces wasted computation on masked positions. After the mask call processes, number of steps is into mask block M1 rows, start M is advanced to the first fully unmasked row block. From that point, every entry in our column block is valid, so the unmask call runs at full efficiency with the larger block M1 tile. After the mask call start M is advanced, the unmask call begins immediately below it. In the non-causal attention, we don't need to think so much. All Q row blocks strictly below the diagonal I greater than J. Rows that unconditionally attend to key position J are processed without thinking. So we are specifying start M equals to 0. So this single call covers the entire sequence. For causal attention, it covers everything below the diagonal. Now this overall point about start M is slightly complex and confusing, so I want to cover that in slightly more detail. This part of the logic is not that much obvious. For this, I'll go to the blog. Where it is explained in detail. Now let's take a concrete example where n is 8, block N1 is 4, block M1 is 4, mask block M1 is 2, and block slice factor is also 2. Now consider the full 8x8 attention matrix where rows are, so these rows are the query tokens and columns are the key tokens. So this is J and this is I. So causal masking means token I can only attend to token J if J less than equals to I. So for example here J is 4 and I is 5. So this holds, that is why it is we can do this. But for example here J is 6, I is 2. So this does not hold and so this is cross. So let me remove this. So now notice that some blocks blocks where rows are fully masked, some blocks where rows are fully unmasked, and then there is partial. So we need to process it accordingly. Now let's consider a case with both masked and unmasked rows. So n is 16, m is 16, like here. So you can see this triangle here. Okay, you cannot see anything. This triangle will be the diagonal mask. So in that case, start n here is 4 and number of steps become, my block n is 4, mask block m is 2. So that means 2 steps of size 2. So here you can replace by 4 and for start m we can replace by 4 and number of steps is 2 and so previous value of start m is 4, so plus number of steps into mask block m is 2 into 2 is 8. So next start m will start here at 8, right? So all the rows above the diagonal are 0 and can be skipped. So start m starts at start n. So this one we can skip, right? Because that is the first query row that has any non-zero entries in our column block. So we process this and we can say that all of the, or rather, so we start here and then we process the remaining as fully unmasked. After the mask call finishes at start m8, the unmask call picks up from there and runs to the end of the sequence. So we take the causal part here and then run the non-masked to the end of the sequence. Now that we have done this, we can write dv directly, but for decay there is a tau factor. as we can see here. Hence we need to scale by SM scale. Once here, applying it as a single scalar multiply can fully accumulate block N1 head dimension buffer and is more efficient than multiplying inside attention backward DKDV at every iteration, because each program instance owns an exclusive J indexed region of DKDV. Atomic write is not required. In the DQ part, after the DKDV work is done, the same program instance can reuse its execution slot to also compute DQ for query row block, i.e. is PD. So that is why start M is PD into block M2. The grid is sized so that N by block N1, N by block N1 is the same as N by block M2, meaning PID maps equally to both KV column block and Q row block. We load Q and DQ. We load Q and DO and the log sum exponents slice M, which we also reshape as block M2 for broadcasting across the block N2 column dimension in attention backward DQ. So similar to how we have discussed before, query row I can only attend to key columns j less than I. Hence we process the diagonal block first, as we just discussed, with mask equals to true, and the finer tile mask block N2. After the mask call, end N is set to the start of the mask region and start N is set to cover the remaining unmasked columns, where as you can see here, j will be less than the diagonal. The backward scanning direction, when we start from the diagonal and move left, so we are moving left here, is arbitrary. So we want to keep, so similar to, so for DKDV we went from up to down, right? Or if I show here, in DKDV we came from up to down, so we saw the mask first, then we see the diagonal, and then we got the unmasked. Similarly, for DQ parts, we go from like this, so we get the same pattern. We are keeping the loop structure similar to DKDV layout for code reuse and understanding rather than any numerical necessity. So basically, after doing this mask true part here, right, we go ahead and compute for mask equals to false. Now in the forward pass, we needed to store two separate vectors per row. The first one was Li, which was the running sum of exponentials, and Mi, which was the running maximum. In the epilogue, we combine them together into a single vector replacing Li and Mi, and thus have a single write to HBM. This is because reading and writing to HBM are done in chunks. Hence, writing once is better than writing twice, even though it's the same number of values underneath. Also notice that the forward pass uses exponential 2 math instead of direct exponential, Because of NVIDIA hardware, exponential 2 maps to a single native instruction ex2 dot approx, while exponential, so the exponential is emulated as exponential 2 of x divided by exponential of 2 in software requiring an extra multiply. To use exponential 2 while computing what is mathematically exponential, we pre-fold the conversion factor. So in the main backward method, we have an RCP ln2, and then we have k carrying SM scale into RCP ln2 factor, that is k is multiplied with this factor when loaded into the backward kernel. So this argument k is loaded here in the backward kernel. This is done so that directly when we are doing TL dot k into q transpose, we get tau into kj qi transpose directly into RCP ln2, which means this one we get divided by this guy, we get divided by ln2. And then we can just multiply to restore to the original. This pre-scaling of k helps us cover two per multiples, one for the exponential and one for the scale, with a single post loop multiplication on the final accumulated buffer. This saves arithmetic instructions proportional to number of steps in the kernel. Number of steps. With this, we are done with all the steps in the Triton kernel. Now before closing, let's go over the benchmarking once. We run our code over GPU NVIDIA 800, which is 80 GB and HBM3 memory. PyTorch is 2.10 on CUDA version 12.6 and Triton is 3.6.0. We do our benchmarking across different with batch 2 different head sizes, sequence length and dimensions. So our error graphs are mostly here at the range of 10 to the power minus 4. So at sequence length 256, the naive FP16 and was able to achieve 3.6 teraflops. Ours was around 0.04 ms and 7.6 teraflops. So ms should be lower, teraflops should be higher. It should be doing more and with less time. The PyTorch SDPA is of course the winner here. More optimizations we are getting. So SDPA FP32 is 0.03 with 8 teraflops, and in FP16 it is even better, 0.01 ms at 25.32 teraflops. Sequence length 512, naive one is 0.08 13.22. Our implementation is 0.03 FP32 is 0.06, so beating the FP32. But of course, the SDPA 1 is 0.02 ms. Interestingly, if you see here, at sequence length, so you can go over this. So at sequence length 2048, our values 0.05 381 teraflops is beating the SDPA benchmarks, right? So it's not like writing kernels by hand is bad. You can see here that by writing our kernels, we were able to beat the SDPA for specific workloads. So you can see the same at the graph as well. Our implementation is quite is somewhat better than the SDPA FP16 on H100. This is probably because Triton does auto tuning at the block level. Torch SDPA also does auto tuning, but that is at the implementation level and tries to find the best implementation. Also notice the last one. All the tiled implementations stay flat at around 133 MB. Regardless of n, confirming the ON memory scaling, the naive hits this one, right? 2 GB at 4096 and is approaching out of memory fast, even for a small sequence length with N4K at just 64 dimensions. In FP16 alone, the number of bytes is reaching around 1 GB. So the gap between tiled approach and naive approach, or flash attention and the naive approach, will widen quadratically as n grows. Finally, our video is done. In this video, I have worked through the derivations behind the forward and the backward pass of flash attention. So if you are running on newer hardware such as the Ampere, Hopper or the Blackwell GPUs, then replacing your SDPA attention with flash attention is one of the easiest boosts that you can do to your LLMs. In a future discussion, we will go through the improvements. So this is just flash attention 1 is what I discussed here. So we'll discuss, but till now there is till flash attention 4. So maybe in a future video I'll discuss the improvements made there.